Brendan Robert. I am an architect and software engineer, and today we're going to talk about software repair. We will discuss software repair by breaking it down into definitions, the phases of development where it occurs, the problem causes, diagnosis and triage, repairing the damage, and finally, prevention and hindsight. What is software repair? Jarzobec defines it as a software maintenance that's mostly about change, either to fix bugs or to better satisfy users. Fred Brooks describes it as much of the effort in modern programming that goes into testing and the repair of bugs. Jordan describes software repair in that most programs are changed during their lifetime to be bigger, faster, more extensive, etc. Some examples of software repair are undetected typographical errors that sneak their way into production. The big red ball, the customer says, I would like a ball. And the consultant says, okay. And then they come back and the customer says, no, I didn't want that. I wanted it to be green or red or something else, and so on and so on. So the problem here is that the consultant is spending a lot of trouble and effort trying to appease a customer who's giving incomplete specifications. The lesson learned is that you have to ask the right questions in the initial conversation or you'll never get anywhere. When does software repair happen? Rylick defines many software development phases, and in each of the phases there's a different degree of repair that is required, if any. For example, during initial development, major changes are made to the overall design and they're far less expensive, and really, honestly, it's more likely to just throw out the whole thing and start over again than it is to fix up a little bug. The evolutionary phase is more about re-architecting and refactoring, but there's a lot of bugs that are fixed as well. And actually, as Oren and Wilson pointed out, there's a lot of analysis that's left to be done in this area because really there's an issue getting developers to report all the defects that they find during this phase. The servicing phase primarily focused around servicing repair of defects in software. It's less common for any major architectural changes to occur at this phase. This is where resources are getting ramped to more maintenance developers and possibly people who are not necessarily as experienced with the system. At some point, the servicing hits this evolutionary dead end where it's no longer feasible to make any major changes or accept any more major requests from the customers, and which leads to the next phase of software, which is phase out. During phase out, the security defects are really the only things left to worry about. And I think a good example of that is Windows XP or Windows 7. Microsoft is only entertaining the bugs and the fixes necessary to prevent their customers from getting hacked. Otherwise, they're not adding features. They're not, I don't even know if they're going to bother porting browser platforms to that anymore. So, the phase out is when there's already another product in the works or already another product available, and what they're really trying to do is get customers to upgrade. Closeout is when software has reached the end of all support, and it's either fallen into complete disrepair or the company that owns the intellectual property has decided that it's no longer valuable intellectual property and they're going to gift it to the community, either for software preservation or to let the community own that software. And I think a good example is how StarOffice has become OpenOffice, which has been forked into LibreOffice, and now it's a very vibrant software product, whereas when it was StarOffice by Sun Microsystems as a commercial product, it could very well have easily died on the vine. Why do these problems occur? Well, I think Bill Vaughan says it best. To err is human, and to really foul things up, it takes a computer. Problems can be defined, according to Fred Brooks, as either essential or accidental. So essential being, of course, the indisputable requirements that are necessary for the system to deliver, and the inessential or accidental factors being things such as implementation decisions or, actual bugs. In that sense, not everything perceived as a bug is a result of what's, could have actually been an incorrect decision or accident, but rather it could have been sometimes a symptom of a fragile system that was built on top of a shaky foundation. Issues can also result from misleading or poorly written or incomplete specifications, which result in sometimes catastrophic design decisions. In turn, these incorrect design decisions result in a lot of repair and rework. Or as Brooks says it best, no other part of the work so cripples the resulting system if done wrong. That some of the trickier problems that stem from essential problems such as complexity and visibility where one change could result in a cascade of other problems that are difficult to determine, or even worse, it's unclear what parts of the code relate to what source change and why they're there, as Jarzobec states. Here's an example of an essential problem. Atari secured the rights to a new hot movie property called E.T., and they had very little time to get this product to the market. In fact, they only had 6 weeks. Unbelievably, he completed this in 6 weeks. They had to forego testing. They had to forego all kinds of things that are considered best practice. As a result of having no time to do proper testing, many of the bugs went unnoticed until production. All these things put together resulted in a huge market disappointment. Now, for an example of an accidental problem in code, let's talk about every line of JavaScript you've ever written. JavaScript is, as far as languages go, it's a little fragile. Also, unless you have something going behind you to make sure you're not making easy mistakes, it's very difficult to know where you've gone wrong until it's almost too late and then you have to start over again. How to identify the cause of a bug? Jordan in 1975 wrote that automated retesting is a valuable way to quickly and easily spot issues that creep into code. But these tests only work if the developers actually write them. And even in 1975, developers complained about what developers always complain about, even today, which is that writing tests is a lot of work. Sometimes 2 to 3 times more work than they spend actually writing the code that they're testing. We don't have a unit test telling us what's wrong. What do we do about it? Well, the first thing you do with any kind of, for example, production issue is you want to reproduce it in a way that is something that you can study. So you don't want to necessarily try to triage it or track it down in a production server. You first want to see, can you do this in a local environment, somewhere that you have complete control over, somewhere that you have a better lens. And so by doing that, you're taking the problem away from the production environment, and then you're able to put hooks in, you're able to attach tooling to it, and you're able to do all these other things to kind of get a better focus on the problem. Reviewing a log file is not the fastest way to spot a problem or to triage it, but sometimes it's your only option. And in the case of a problem where you can't reproduce it locally, sometimes it's your only option, period, especially since a lot of problems that occur in a production environment are related to factors you can't reproduce locally, such as disk filling up or out of memory or all kinds of factors like that. Once we've found the problem, we're already 2/3 of the way there, believe it or not. How do you fix these problems once you know where they are? Chris Hadfield says it best: there's no problem so bad you can't make it worse. Just because a bug is reported doesn't mean it's going to be addressed right away, if ever. Now, that's not to say that reporting a bug is a bad idea or a waste of time. In fact, far the opposite. Whenever something is in a closeout or an initial design phase, the bugs aren't usually a major concern unless there's some really pressing obligation to fix them anyway. However, there's a lot of cases where the product owner who's responsible for the backlog of the work being done would take that bug and say, you know what, this person's right, this is a good idea. They might already be developing another phase of another product that's replacing, or they might be doing an initial design phase for the next version of something. And then what was a bug in one sense becomes a requirement for the next phase. In 75, Jordan wrote a list of steps which is still very applicable today. You should study the program. You should understand the existing documentation, if any. You should try to improve it if it's missing or lacking something. And you should be very careful that the changes you're making are isolated to the change that you're looking for. If you do remove any code, you should make sure first that there's nothing else that's using that code. Now, in 75, that was a very difficult thing to do because they didn't have the tools that we have today. Today, it's very easy to look for usages of a given function and realize whether or not it's being used. In the modern programming best practice, before you make changes to code, you should first write a unit test that asserts the expected behavior of the code. The first thing that test will do is fail, because currently the code is not written that way, if it's even implemented at all. Then, once you've made your change, that unit test should then pass. Likewise, if there's any other cascade effects, before you've made this code or before you commit this code to the repository, you should also make sure that any other auxiliary cases that code might affect are also covered by unit tests. That way, over time, you can resolve any fragility concerns in the code by having adequate test coverage across the board. In 1992, Opdyke wrote a paper on refactoring, which has become very heavily referenced across the industry. Of all the things that OPEC talks about, one of the easiest things to apply is the do not repeat yourself principle. And that is, if you see the same lines of code copy and pasted everywhere, get rid of them. Put them in one function and have everything else call that one function. That way, you have one place that logic is occurring, one test to cover it, and everything is protected by that. Lastly, don't leave dead code behind. If you see code that's not being used, whether it be a branch in a conditional instruction that never results to true, or whether it be a function that's never being called, your best strategy over the long term is to get rid of that stuff. One, if you're using a source code repository, you can go back to the commit history and you can see that old code. So leaving dead code behind for reference purposes is actually an error in thinking. Secondly, and more importantly, if you leave this dead code behind, somebody might come along with the mistake of thinking that this function actually works. And if this code doesn't even have coverage, then that's a ticking time bomb. And you can avoid that altogether by just getting rid of it. Okay, so now we've learned our lesson, we've fixed our bug. How do we stop it from happening? Well, you really can't. That's just part of the industry. But there are some things you can do to lessen the impact and the severity. The big one from Wilson and ORM is to hire knowledgeable people, especially in the beginning phase of a project. If you have a really good architect that stops you from making critical design decisions in the beginning, you can save yourself a ton of rework down the line. Jordan wrote about defensive programming back in the 70s, and I think that Jordan's advice on defensive programming is truer today in the online world than it ever was before. You should always sanitize your inputs. This prevents a lot of security vulnerabilities from creeping in. Also, unit tests, making sure that people follow adequate test coverage, really helps prevent a lot of fragility over time. You should use the right tools. Using an IDE that's designed for your language and frameworks, it's going to make a huge difference. Fred Brooks wrote that program verification is also a good strategy, especially for the core systems level, like operating systems and drivers. But the issue with program verification is that it requires so much overhead to do correctly that you might not get any time savings out of it. You're just going to buy stability for your investment of time. And finally, the last way you can prevent bugs is to solve the complexity problem early by using modern frameworks that are well tested and well supported. For example, Jarzabek wrote about XVCL. It hasn't really caught on. However, if you look at the specification of XVCL, it looks a lot like Spring. In fact, I would even venture to say that Spring is based on a lot of the things that XVCL was proposing. Thank you for taking the time to watch my presentation. Please, if you have any questions, feel free to send me an email or hit the comments or the like button down below.